Our first speaker is Jean-François Nierengarten. He is European co-chair of the Advisory Board of Chemistry, a European journal. He is Director of Research of the CNRS and head of the Laboratory of Molecular Materials at the University of Strasbourg in France. He received his PhD with Sauvage and Dietrich Buchecker in Strasbourg, did a postdoc with François Dierich at the ETH in Zurich, and has been in Strasbourg and the CNRS since 1996. His research excels in the chemistry of fullerenes, macrocycles, and dendrimers in material science and biology. Today, he will speak on fullerene and pillarene scaffolds for the preparation of advanced materials and bioactive compounds. Jean-François, please give your lecture.
Thank you very much, Ken. Thank you very much, Imo, and all the the editorial members of the journal for the invitation. It's a great opportunity to talk to you today. And it's a special occasion because it's the anniversary of the journal. So my talk will be a kind of special. I will try to show you how important was that journal in my career. And I will not mainly focus on the latest data. So I will switch to the screen now. Okay, here it is. Can you see my screen? Should be fine. So it's a very special occasion, and I'm very pleased to give a talk today for this special event for the journal. I remember 25 years ago, I was in Zurich as a postdoc with François Dietrich, and that new journal appeared, and we were receiving Chemistry European Journal attached to Angewandte Chemie during, I think, 1 or 2 years, it was like that. And I remember very well the very first paper of François in Chemistry European Journal. It was a work of my lab mate, Rüdiger Faust, and we had a discussion with François. We said, okay, what's the new journal? And François told us, but you know, that journal will be the very important European journal for the publication of full papers. And I think he had a very good feeling because 25 years after, we see all the work that has been done, and it's a reality. So my first papers published in Chemistry European Journal were, of course, from my postdoc time with François, as he was a very strong supporter of the journal. We prepared some rotaxane, we Fullerene stoppers, some...
We cannot see your slides, unfortunately. You need to start sharing your slides. Sorry to interrupt.
Let me see. You can see my slides now?
Yes, yeah, perfect. Thank you.
Okay. So, during my postdoc time, we published 2 papers in chemistry, as François was a very great supporter of the journal since the beginning. Yep. And of course, when I started my independent career, I started to follow his advice, and I published in Chemistry European Journal. And my very first paper in chemistry, that's an old story. It's a liquid crystalline fullerene supermolecular derivative. We sandwiched the fullerene in between 2 macrocycles to generate liquid crystal. What was nice as well, the concept papers, that was a new kind of papers that were proposed by chemistry, and I like it really a lot. You can propose, you can present concepts from your lab after a couple of papers to show what direction you are studying. It's really a very nice, it was a very nice initiative, and I still enjoy a lot this kind of papers. Of course, fullerene chemistry, that was the main aspect of our research 20 years ago when I started my independent research. And in the beginning, we were mainly interested in combining fullerenes with all kinds of donors, as fullerene is an electron acceptor, to observe photo-induced electron transfer, photo-induced energy transfer, and that's a good collaboration with my good friend Nicola Maroli in Bologna. And of course, many of those data were published in the journal. In recent years, we started to use the fullerene not for its electronic properties, but for its structural property. You can functionalize the C60 with 6 addons, and if you use the nice chemistry developed by Andreas Hirsch in Erlangen, you can produce fullerene hexaduct. You control the position of the 6 addons on the fullerene. And when you see, you have a very compact scaffold where you can graft up to 12 functions. The preparation of fullerene hexaduct is not always very efficient, especially when the starting materials are a little bit fancy. So there's a big limitation in the preparation of this kind of materials. And what we have developed are clickable fullerene building blocks. They are quite easy to prepare because we prepare them from simple building blocks, and then you can graft whatever. And if you use the copper catalyzed alkyne azide cycloaddition, you can obtain almost everything in very good yields. We have been quite successful by grafting sugars around the fullerene to prepare what we call fullerene sugar balls. And I think most of our data on fullerene sugar balls have been published in chemistry over the years. We have shown that you have very strong multivalent effect for the binding towards bacterial lectins, and those compounds are potential anti-adhesive agents to fight against bacterial infection. You can also use them in a smart way as multivalent enzyme inhibitors. We have shown very strong inhibition, multivalent effects in enzymatic inhibition, which was quite unexpected in the beginning, but now it's a field that is intensively investigated. More recently, we switched a little bit from fullerene chemistry to pillar 5 arene chemistry, and I would like to present you one example of our pillar 5 arene scaffolds in more detail today, but just an overview of what we have done. Again, pillar 5 arenes are quite easy to prepare if you use the conditions developed by Ogoshi. You start from hydroquinone building block. Under acidic condition and Friedel-Crafts conditions, you produce the pillar 5 arene in extremely good yield. We can prepare grams of it in a couple of days. The key here is that the Friedel-Crafts reaction is reversible and the formation of the macrocycle is under thermodynamic control. And that explains why the yield is so good. After, of course, the cyclization is very sensitive to sterics. So it's very nice to start from a simple building block and then to post-functionalize. And to do so, we can then transform the bromides into the azide, and we can use the click chemistry. It's working very well. You can prepare almost whatever you want. You can also use other reactions. That's not an issue, but the click chemistry is very nice for that because it's high yielding and selective, and you can use almost all functional groups except azides and alkynes. Of course, our building blocks are symmetrical, and it's very complicated to change one functional groups and to keep the others identical. So the big advantage here is that you can prepare host-guest complexes, and for that you can prepare then rotaxane, so you can keep symmetrical compound. You can graft 10 functions onto the pillar 5 arene macrocyclic component, and you can use stoppers. You can use 2 identical ones or 2 different ones to introduce different functions. For that reason, we developed very efficient strategies to prepare pillar 5 arene rotaxanes. They are based on stopper exchange reaction, and that was also published in chemistry. So having those scaffolds, we use them for many applications in biology. For example, we grafted ammoniums to prepare polycationic pillar 5 arenes, and they interact very well with DNA, and we could use them for transfection. You can also use them to prepare glycoconjugates, and again, the multivalent presentation of ligand is very important to achieve high affinity towards bacterial lectins. And we took profit of the formation of rotaxane to incorporate 2 different sugars, and that way we could target the 2 lectins of one bacteria with very high affinity. One lectin is sensitive to multivalency, so that's why it was important to have 10 copies of the blue sugars. The other lectin is not sensitive to multivalency, and 1 or 2, here the 2 stoppers are sufficient to achieve a great affinity. We also spent some time to organize those compounds. We prepared some liquid crystals with my colleague Robert Deschenaux in Neuchâtel. We grafted Pershek-type dendrons, and we could self-assemble kind of nanotubes that are liquid crystalline. To prepare Langmuir films, we prepare rotaxane. On one side, we put a polaride group, like that you can anchor the compound on the water, and we form very nice Langmuir films, and we could show that the mechanical bond here has a very strong influence and is at the origin of phase transition in the thin films. And of course, we also used gold surfaces to prepare modified electrodes using self-assembled monolayers to do some ultra-fast electrochemistry. And all those data are published in chemistry. And now I would like to show you one example a little bit more in detail. We grafted also porphyrines onto the pillar 5 arene. At the beginning, it was okay to prepare a kind of light harvesting system with the 10 porphyrines, because if you look a little bit at the way you can organize those porphyrines around the pillar 5 arene, it reminds you the way the Iims are organized in the photosynthetic center. So we prepare the compounds, and here you can see the enantiomer of the free base porphyrin system. It's a little bit broadened at room temperature, which is normal for such compact molecules, but when you increase the temperature, the spectra is normal. If you look at the UV, there is not much to tell. It's exactly what you expect for a system with 10 porphyrins. It corresponds to the sum of 10 times the molar compound. So it's just the decaporphyrin system. The situation was a little bit different with the zinc porphyrin. The spectrum at room the enantiomer spectrum at room temperature is quite broad, but at high temperature, again, it's very similar to the free base porphyrin. But now if you look at the UV, you have a splitting of all the bands. And typically you have such a splitting when you have an electronic coupling between the porphyrins. But how can you have an electronic coupling when you have the zinc and not when you have the free base? So that's not the explanation. Actually here you have a triazole ring. The triazole ring is a ligand that is able to coordinate the metal of the porphyrin. And that's why you have that splitting, because you have a partially coordinating, you have the porphyrins are partially coordinated in an intramolecular fashion by the triazole. In a way, it's partially coordinated. At room temperature, you have a fast exchange between coordination, decoordination. When you increase the temperature, it becomes faster, and eventually at the end, you have a completely open structure. Of course, when you cool down, you favor association. You have a fully associated molecule, but you have no preferential conformation. You have a broad spectrum. TISU was also supported by DOSI NMR experiments. We measured the DOSI of the free base, then of the zinc porphyrin system. And if you look, you have a volume reduction of more or less 30%, which is consistent with a partial folding of the molecule. Can we control that folding, unfolding? That was our challenge. And the answer is yes, if you use electrochemistry. For the free base, you have nothing special. Like for the UVs, it's a simple decaporphyrin, and the porphyrins are all independent. But if you look for the zinc porphyrin, you see that you have a splitting of the waves. So it's a little bit more complicated. So in order to see what's going on here, you have a model porphyrin, and you see that the first oxidation in particular here is split it into two waves. Not the second one, but the first one. And it's the same for the reduction. So to understand what's going on, we did some binding to see how the apical coordination of the zinc porphyrin influence the electrochemical properties. So in pink, you have the starting zinc porphyrin. If you add one equivalent, you see that you have a splitting of the first and the second oxidation. And when you add two equivalent, you have saturation, and you see that your system becomes easier to oxidize upon coordination. It makes sense. You increase the electronic density of the system by the coordination, so it's easier to remove an electron. And if you look now at the second oxidation, it becomes more difficult. So coordination stabilizes the system. So that, in other words, is upon oxidation, you have a stronger interaction of the imidazole with the zinc porphyrin. And now if we look at the big system, you see that you have a first oxidation, that's the coordinated one. The second oxidation is the uncoordinated porphyrins. At that stage, you have the decacation. You have a completely folded system because you increase the stability of the system. And at the second oxidation, here it's at the typical position or redox potential of a coordinated system. So it's completely folded. Now in the reduction, first a look at the model compound. It's the other way around. Now you see that upon addition of the imidazole, the first reduction becomes more difficult. That makes sense. You increase the electronic density of the system by the coordination. It's more difficult to add an electron. And if you look at the second reduction, there's no difference almost. That means that upon the first reduction, you have decoordination because the system becomes completely unstable. And now if you look at the big system, you have first reduction of the uncoordinated, reduction of the coordinated ones, and then you have a complete decoordination, and then you see a second reduction of the regular zinc porphyrins. Of course, we used imidazole as a model compound, but imidazole is a much better ligand than the triazole. So we wanted to see if we can displace the intramolecular interaction by using by adding imidazole to the system. And here you see the NMR binding study. You see the broad NMR due to the folding unfolding that is dynamic at room temperature. And when you add the imidazole, you see at the end you have a very nice spectrum because you have completely disconnected the triazole, the intramolecular interaction between the triazole and the porphyrins. We could also follow that by using DOSI experiments, and that's the DOSI spectrum recorded upon addition of a large excess of imidazole. You are saturated. Here you can see that you have an excess, that's the uncoordinated one. And if you look at the diffusion coefficient, you see that you have volume expansion of 49%, almost 50%, when you go from here to the system that is completely open upon addition of the imidazole. You can also monitor that easily by UVVs. Here you see how the system is completely open now upon addition of the imidazole. And you see that in the beginning you have in black a splitted Sorel band, and at the end you have just one. And if you compare now with a model porphyrin to which you add the same amount of imidazole, you see that you have a perfect match between the spectrum. So as a kind of summary, it's a kind of molecular flower. It's partially folded in a neutral state. When you oxidize, you completely close. Of course, it's reversible. You can reduce again to go back to the neutral state. You can reduce to prepare the decaanion, and then it's completely open. You can, of course, go back to the neutral state, which is partially folded. If you add a chemical input here, an imidazole ligand, you completely open the system, and here you have the molecular flower. And of course, that was a perfect cover page for chemistry, and it's also a nice occasion to thank the journal and to celebrate, because it's the 25th anniversary today. So cheers to everybody. And when I see during the 25 years, of course, we were publishing a lot in that journal. It was always a pleasure to work with the editorial team. I think that I would like to thank all the people who did a fantastic work to set up this journal and to bring the journal at the level it is today. So there is the editorial team. You have the editor-in-chief. Now it's Aimo. Before it was Neville. They did a fantastic job, both of them. And really, I hope that for the next 25 years, it will be even more successful. So to finish, I would like to thank my collaborators. I mentioned a few of them during my talk, but of course we are doing mainly synthetic chemistry, a little bit of physical organic chemistry, but most of the biological studies or material science applications are done in collaborations. I have to thank all the people who did the work, in particular all the students, and in France we are lucky to have permanent people, so I would like to thank Michel Holler, Uwe Hahn, Mathieu Chessé, Ivona Nierengarten, that are doing a fantastic work in the group. To do research you need money, so I have to thank a few institutions, the University of Strasbourg, the CNRS, and in particular the foundation we have in Strasbourg. They are very supportive. And thank you very much for your attention.
Thank you very much, Jean-François, for the wonderful lecture with magnificent illustrations. Thank you.
Thank you.
And that actually prompts my first question. You had a number of animations of your molecular flower and of coordination and of changes from unfolded to folded structures. And I wonder whether those were based on molecular dynamics or crystallography, or what is the origin of those movies you were showing?
It's just a cartoon. Sorry, it's just a cartoon to illustrate. We have done some molecular modeling, but those are big systems, and we are quite limited. So we calculated the structure at the PM3 level, which is fine for such a big compound. You see that what we claim is reasonable.
Okay,
but we haven't performed high-level calculations or dynamic simulations. But the systems are quite big. Yeah?
Another more specific question has to do with your showing there was an unfolded and folded structure. And it was clear from the illustrations that the folded was a very compact structure. Is that based on your NMR evidence, or how do you deduce that change?
It's you can follow that by different ways. We are sure that it's an intramolecular interaction between the zinc porphyrin and the imidazole from the DOSI experiments. It's not intermolecular. By UV, you can see that when you lower the temperature, you increase the complexation, because you have a very nice redshift of the SORA band upon complexation. So it's very easy to monitor. It's very sensitive. You change the temperature by 5 degrees, you see a change in the ratio. Okay. At high temperature, you of course you favor dissociation, and you see that you have almost no complexation anymore. All the techniques are pointing in the same direction. It's not just one technique that is giving an answer. In electrochemistry, we see the difference in redox potential between the folded and unfolded. It's in NMR, we can see that you have a change based on the temperature, and UV is very sensitive as well.
Okay, thank you. Okay, several questions online. One from Jeremy Barreau, who says, nice presentation. And a question about, doesn't zinc go into the octahedral structure when you add imidazole derivative?
Oh, yes, you can, but if you do regular binding study, you see that the first binding is the binding constant is quite high, and the second is not. Of course, if you put a large excess, you will start to see it, but the second binding constant is very weak.
Okay. Another question, but this is more of a technical one about your presentation, from Dheeraj Shetty. And the question is, which software was used to show the molecular flower? I'm using Mac, and all those animations are done with Cheetah 3D. I see, okay. Thank you. A question from Shinaraja. How difficult is the synthesis of the macrocycles in pure form? Are template methods useful? Oh, the pillar 5 arene, you have a template. The solvent plays an important role, because when you prepare the pillar 5 arene, if you use methylene chloride, or then you favor the cyclopentameric system. But if you use a larger solvent like chloroform, you start to favor the pillar 6 arene. So you have a kind of templation from the solvent. So the solvent is very important, but the yields are good and the purification are quite easy. But for the post-functionalization, once we have the azide, you have to, if you want to click 10 times or to functionalize 10 times the same scaffold, and it's the same story with the Fullerene, where you have to perform 12 reactions on the same scaffold. The purity of the starting material is essential, because if one of the two starting material is not pure, at the end you have nothing. So that's very, very important. You have to be very careful with that. And one last question, I should know the answer, since I had the fortune to be a colleague of François Dieterich at UCLA many years ago. And Yves Rubin, of course, is my colleague now. And it has to do with the structures of the fullerenes that you showed. You showed nice hexa-substituted fullerenes, and I wonder, are those pure isomers, pure regioisomers, or are they mixtures?
Yes, those are pure isomers. If you look at the structure of that particular hexaadduct, you isolate 6 benzene rings that are a little bit flattened in the structure, so you have 8 times the local aromaticity. And compared to all the others possible hexaadducts, it's the most stable. So you have to work when you prepare the hexaadduct under thermodynamic control. That's very important.
Okay, thank you.
And
I ask you one more question, and that is from Antonis Karalius. He had 2 questions, but I'll just ask you one. It has to do with whether there was any observed supermolecular chirality when the 2 faces of the Fullerene, when sugar functionalized, are slightly different. Was there any observed difference in, for example, interactions and reactivity when functionalized with sugars?
That's a good question. Yes, the pillar-5 arene macrocycle is chiral, is C5 symmetrical, D5 symmetrical, sorry, and it's a chiral compound. When the substituents are small, you can have racemization, but of course, when you put the sugars, you have diastereoisomers. But we were unable to separate them, and for those compounds, we use the mixture of diastereoisomers. But I would say that the linkers were quite long, and there was no evidence for a chirality transfer even in the enamel of the final compounds. We have done some with other chiral groups that were closer to the pillar-5 arene, then you could separate the diastereoisomers.
Thank you very much. So I think we would all like to thank you, and I hope you can hear the thunderous applause coming from all over the world. Thank you very much, Jean-François.
Thank you.